Okay. All right. Okay. All right, let's, I know I gave a whole bunch of stuff to you guys. I gave a bunch of stuff back to you. Go ahead and set it aside for now. We can talk about it another time. Yes, sir.
When were these? Are these due already?
Yeah, I haven't even given them out to the other classes, so keep working on them.
Oh.
Yeah. Yeah. Oh, good. Yeah, maybe at the end of class. Yeah. Or before you leave today. Okay. Today, what we're going to do is we're going to go over some of the homework. We're going to go over some of the homework problems, but I was actually thinking that it would be better to wrap up everything we need to know about velocity and acceleration and position. Wrap up everything about object motion first, and then we'll finish up with going over some homework problems. I don't know if you have noticed yet, but these problems, especially in the homework, they really weave with each other. It's not like there's separate knowledge within object motion. It's all the same thing, and it all fits together. I just have to teach it to you in pieces because you can't digest the whole thing at one time. Okay? Now, if you have not watched the video that I made last week, I thought it was a pretty good video, by the way. Did anybody get a chance? Just curious if I can get an opinion from anybody, if anybody did have it. It was day 22. And I went over a bunch of homework assignments, and then at the end, I was super duper rushed. So then, but they were really easy concepts. I basically went over speed, I went over average velocity and average acceleration. And if you watch the video, you can get the lesson itself in probably about 10 minutes. Because average velocity and average acceleration are very easy concepts. They relate directly to average rate of change, which is f of b minus f of a over b minus a. I know it's been a while since we did that, but it's all based on that. And then I talked about how to know when an object is speeding up or slowing down. And the nutshell there is an object is speeding up if its velocity and acceleration have the same sign. If acceleration and velocity are both negative, it's speeding up. If acceleration and velocity are both positive, it's speeding up. If acceleration and velocity have different signs, then it's slowing down. There you go. If acceleration is negative and velocity is positive, it's slowing down, and vice versa. That's all you have to know about speeding up and slowing down. Okay? So today, what I want to wrap up with is I want to talk about maximums and minimums of position, velocity, and acceleration. And then lastly, I want to talk about displacement, which is also called change in position, and total distance traveled. Okay? So, because there's a difference between these two, and they both relate to, does anybody know, if these two things related to only one of these three functions, which one would they relate to? No, well, it's okay. You don't have to, it was a good guess. You take a risk. We take a risk. Take a risk. Position, yes, they relate to position. Because displacement is the idea of leaving one place and going to another place, leaving one position and going to another position. Total distance traveled is how much position you have covered exactly. Okay? So, let's start with maximum and minimum. There are questions that will ask you about a maximum or a minimum of one of these three things. For example, there might be a question that says, what is the maximum acceleration? Okay? Or it might say, what is the maximum velocity over an interval? Or it might say, what is the maximum speed? I'm pretty sure you've already seen what is maximum speed at some point. And then, there aren't any questions that ask us about maximum position. Why would they not ask us, why would they not say, hey, what's your maximum position? Not necessarily. That's a good try, because it could be. Your position could just be going on and on and on and on and on. Reference? In a way, that's right. In a way, it doesn't give you a point of reference. Although saying maximum or minimum do not tell us based on the starting point or the point of origin. Also, if somebody walked up to you and let's say a bunch of people were playing in a field and they said to you, hey, what was their maximum position today? It wouldn't make sense, right? It doesn't sound right, okay? So we don't say maximum position. Instead, we say things like this. If we want to talk about maximums in terms of position, okay, we say things like this. Ready? We will say things like, when is it at its highest point? You know, like you shoot an arrow. They got all these problems where you shoot an arrow up in the air. When does the arrow reach its highest point? Okay, what's that? H max, that's right, H max. That's correct. Yep, highest point. Or when is at, let's say that you throw something buoyant into the water and you project it so it goes down underwater and then it comes back up, and you want to know what its lowest point was, or how deep it went. They might say, well, how deep did it go? That's a lowest point. Does that make sense? Lowest point. If it's left and right movement, it would say, what is the farthest left the object went? What is the farthest left or the farthest right? Okay? These are ways of saying maximum position. How far forward did it go? How far backward did it go? All of these things, all these questions are asking about the position of the object, and they are asking about either a maximum or a minimum position. When we ask about maximum or minimum acceleration, we usually say exactly that. What is the maximum acceleration? What is the minimum acceleration? When we talk about velocity, we usually say, what is the maximum velocity? What is the minimum velocity? Speed has a few different things. We can say, what is the maximum speed? What is the minimum speed? Or, what are two other words that you might use to say maximum speed? Fastest. Yep. What'd you say? Top speed. Yeah, there you go. Fastest. Slowest. Top speed. Okay? These are all things that you can say to imply. Do you guys know what the word imply means? Imply means you're saying it without saying it, right? When you say fastest, you are implying maximum speed. When you say farthest left, you are implying minimum position. Okay? And that's one of the hardest things I think people have when they do word problems. Most people seem to hate word problems. And I find that one of the things I think people, the reason they don't like word problems is because of all the implied information. They're fine with the explicit information. It's the implied information. It's the implicit information that they usually do not like. Okay. You like word problems? Good. That's good.
Like someone else's there.
Yeah, exactly. Yeah.
Helping me.
My son and daughter, they call them story problems.
Yep.
Yeah. They really like story problems. And I won't tell them that they're called word problems, or that other people call them word problems, because so many people say, I hate word problems. And I don't want my kids to hate word problems. You know, a lot of things in the world are all about, they're all about perception. You know, when you say, you know, manipulate, they're like, no, don't do that. But when you say, you know, help fix or work on, then they're okay with that. You know, it really depends on how you say it. Okay, so yeah, like, you know, when I use this marker up on the board, I'm manipulating the marker. You know, but people think that the word manipulate has a negative connotation, like I'm doing something bad to the marker. Yeah, I'm controlling you. Yeah, exactly. Nobody wants to be controlled, right? Yeah. Okay. All right. So look, let's talk about how would one identify the maximum velocity or the minimum velocity. Let's say let's say that we had a graph here, and let's say that this is a graph of velocity. Okay, and let's say that it looks something like this. This is time, and this is velocity. Okay, so this is a graph of velocity over time. Now, on a graph, could you very easily identify the maximum velocity? Yeah, where is it? It's right there, right? There's the maximum velocity. That's the highest point of velocity, right? Where's the minimum velocity? Right here. Right? There we go. That's the lowest point of velocity. I'm hoping by now you have learned that on graphs, the highest point on the graph is the maximum and the lowest point on the graph is the minimum. Now, granted, if this kept going, right, then the maximum would probably be over here somewhere, right? But let's say that we are stopping the graph. Let's say we're only looking at the graph from 0 to 12. We're only looking at the interval from 0 to 12. So from 0 to 12, that's the maximum velocity and that's the minimum velocity. Okay? So I got a question for you. I want you to look at the graph and I want you to think about this. What is the slope of velocity at its maximum and at its minimum? 0. Yeah, acceleration. That's right. It's 0, right? The slope of the tangent line. Can you see the tangent line? Can you imagine the tangent line on there? If we were to draw a tangent line, wouldn't the tangent line look like that? And down here, the tangent line would look like that. Does that look about right?
Yes. Yeah.
So, if the slope is 0 at a maximum and minimum, what's probably the best way to identify a maximum or minimum? Find out where the slope is 0. Yeah, I'm sorry. And what is the slope of velocity? No, keep trying. I want you to keep trying. Eventually you're going to hit it.
I'm sorry.
What is the slope of velocity? Acceleration. So all we have to do is take the derivative of velocity, acceleration, set it equal to 0, and find out every place where acceleration equals 0. And wherever acceleration equals 0, what would I do with those values, with those t values? Plug them into the velocity and find out whether they're a high point or a low point. That's it. Okay? Should we try one?
Yes.
Okay. Let's use, you know what? Let's go ahead and use that one we just used. Can we use, what was it? T to the, we had v of t. V of t is 4t cubed minus 30t squared plus 48t. All right? And let's say someone says, hey, I want to know the maximum velocity and the minimum velocity. Well, we're going to take the derivative. We're going to find out where the slope equals 0, right? So we're going to do the derivative of this, which is 12t squared minus 60t plus 48. And didn't we already determine earlier that this equals 0 when t equals 1 and when t equals 4? We did determine that earlier, right? We factored it and we got t minus 1 and t minus 4. Okay? So there are only two places where velocity has a slope of 0. So now what do? Plug them into what? Into velocity, right? Because we want to know what the maximum velocity and minimum velocity is. So v of 1, and we already found v of 1, didn't we? What was it, like 22 or something? 4 minus 30 is negative 26 plus 48 is 22. And then v of 4. If we put 4 in here, we get 4 times 4 times 6, 16 squared, it's 256. You might need a calculator, but 256 minus 4 times 16, 16 times 30, 160, 480. Yeah, plus 48 times 4. That's about 50, and 50 times 4 is 200. If we take away 8, that's 192. All right, so 256 minus 480 plus 192. Let's see. Yeah, it looks like 2 448, or sorry, 448. So this and this, 256 and 192 is 448, I think. And then we subtract 480. So that's a difference of, yeah, negative 32. There we go. So when does okay, I'm going to ask you several questions. When does maximum velocity happen? When? Maximum velocity. When time is 1, yep. When time, at time 1, okay, it reaches maximum velocity. What is maximum velocity? 22. Okay. When does it achieve minimum velocity? T equals 4. What is minimum velocity? Negative 32. Okay.
So there's like no units you put behind it?
There will be eventually. I didn't give you units in this particular question. Sometimes they give you units, sometimes they don't. If they give you units, then yes. If we said that it was moving in feet where time is measured in hours, it would be feet per hour. This would be feet per hour. And what does the negative mean? Left. That it's moving left. That's right. Moving right, moving left. Now let's talk about maximum and minimum speed. Yeah.
So this is velocity?
This is velocity. Let's talk about maximum and minimum speed. Speed is the absolute value of velocity. It's velocity without sign, right? What is the maximum speed on this interval?
32.
It's 32 feet per hour, inches per second, meters per second, whatever, right? It's 32 because we're going to take the absolute value of these values. So really now speed at time 1 is still 22, but speed at time 4 is positive 32. All right, you ready for the $100,000 question now? What is the minimum speed on this interval?
0.
0. That's correct. Yes. Tyler, do you want to tell us why it's 0?
Because there's a point when like it's at rest, or it's like using infinite value theorem.
Yes, very good. Oh, that's beautiful. Achievement unlocked. That was really good. I've never had a student volunteer the intermediate value theorem to discuss speed. That was really good. Thank you, Tiger. Okay, by the intermediate value theorem, velocity at some point on this interval is 0, right? And since speed is always positive or 0, it's never negative, right? Because it's the absolute value. There must be a 0 on this interval, and you can't go any slower than 0, right? So the minimum speed on this interval is 0. Okay. All right. Appreciate that, Tiger. Yeah. Okay. All right, now. Oh, now let's talk about what about maximum and minimum acceleration? Thoughts?
Wait, so that was
Acceleration.
That was speed, and yeah, the second part was speed. The first we did velocity. What do we need, Marquise?
You said, wait, you want the maximum minimum acceleration?
Yes.
Wait, what did you
Oh,
just
you
say?
just get the
Oh,
You didn't write anything new?
not really. I just wrote that speed is the absolute value of velocity,
Oh.
and then we just talked through the numbers. Yeah. So if we want maximum and minimum acceleration,
what's like the abbreviation for speed?
I just write speed. Don't use S, because S is often used for position. Yeah. All right, so how would I identify maximum or minimum acceleration?
would it be the derivative?
Not where acceleration is 0. That would tell us where velocity has a maximum or minimum.
That would be the derivative of
We need the derivative of acceleration. Yep. Anytime, here's the general rule. Anytime, in fact, I'll write this. To find a maximum or minimum, you can write this down. To find a maximum or minimum point. This is really only 2 things. Step 1. Find all t where the derivative is 0. Where the derivative is 0. Now I say derivative because it depends on what it is you want a maximum or minimum of. If I want a maximum or minimum of position, then what do I want to set equal to 0? Velocity. If I want a maximum or minimum on velocity, I want to set acceleration equal to 0. If I want a maximum or minimum on acceleration, jerk. It's called jerk. The derivative of acceleration is called jerk. You don't have to know that. I'm just telling you. But you know what? Even if you didn't know it was called jerk, could you still find a prime of t? Absolutely. Just set a prime of t equal to 0. Okay? And find all the t values where that's true. Step 1. Step 2. Plug all t's. Plug all t's into the original function, into, when I say, I don't want, oh gosh, how do I say this? Into the function. I'm just going to say the function. The relevant function, whatever. Not the derivative. If you plug these numbers into the derivative, you're going to get 0. Don't plug them in the derivative. Plug them into the function that the derivative came from. Plug all the t's into the function and find the highest or lowest points. To find the high and low values. The highest value, let's say there's 17 different zeros. You'll find 17 different values maybe. Whatever the highest one is your maximum. Whatever the lowest one is, that's your minimum.
So it has to be on an interval then, right?
Yes. Oh, very good. Here's the other thing. You want to find all t's where the derivative is 0 on the given interval. Okay? Because if one of your zeros, if we told you the interval that is from 0 to 12, and one of your t's is -2, well, that one doesn't count. That one doesn't count. Okay? I did leave one thing out here. Okay? This is because we're going on simplicity right here, and we'll get to it. We'll get to it later, but I'm going to say it now. I'm going to make it official later, but I'm going to say it now. You also have to test, find all t where derivative is 0. You also have to identify all t's. Well, I'm just going to write it like this: endpoints. You also have to test. You also have to test the endpoints, because it's possible that your maximum or your minimum occurs at the very beginning or at the very end of the interval. Yep. Like if we had an interval, if our graph looked like this, and if it did this, right? Check this out. Look, your minimum is actually at the end point. Your maximum is also at an end point. We'll make it more official later. For now, I just want, in general, you to be able to understand this. I believe section 4.2, which we'll cover in like November, is specifically dedicated to identifying maximums and minimums. And that will make it a lot more official then. Okay? All right. Is this okay? Is this maximum and minimum? So far, are we okay? All right. Let's now talk about displacement and total distance traveled.
Wait, so when we're looking for the zeros, it depends on what we're looking for, like what we're trying to find it for, because we use acceleration.
Yes, it depends on whether you want a maximum or minimum for velocity or position. If you want farthest left, that's a minimum on position. So you're going to take the derivative of position, which is velocity, set it equal to 0, and then test all the values in the position function. Okay? So yes, it depends on what you want the maximum or minimum of.
So why would you set acceleration? Why would you find the
Derivative of acceleration? Is that what you're asking?
why would you find all the t where it's 0?
Where what is 0?
The derivative
Which one?
of acceleration.
Okay, you would find where the derivative of acceleration equals 0 if you're looking for a maximum or minimum acceleration. If you want a maximum or minimum velocity, you would set the derivative of velocity equal to 0. If you wanted a maximum or minimum on position, you would set the derivative of position equal to 0. It's whatever you want the maximum or minimum of. You would do the derivative of that function, set it equal to 0.
T for all of it.
Correct. All the places where it equal, all the t's where it makes it equal 0. Now, let's talk about displacement and total distance traveled. I'm going to do something here. Each one of these squares, can you help me out, Bianca, because you're the only one who can really see these squares. I got carpet over here and there in the second row. Each one of these squares is 1 foot. Okay? So I'm going to start off right here. Okay? Can you see where I'm at?
Yes.
That line right there where kind of this leg is, right? I'll be right back. How far away am I from where I started?
Not that far.
Let's count it. There was that line. How many lines? 1, 2, 3. So how many feet away am I?
3.
3 feet away, right? My change in position, 3 feet. I started there. Now I'm over here. Change in position, 3 feet, right? Change in position, another word for that is displacement. My position was displaced by 3 feet. If somebody saw me standing there and then they had a coughing fit and they were looking down or closing their eyes for the whole, 20, 30 seconds it took me to do all that walking. And then they opened their eyes and I was standing over there, they'd say, oh, he moved 3 feet. Right? Is that reasonable? Okay. My displacement. Displacement. Yep. Displacement over an interval, over the interval from A to B, is very simply x of B minus x of A. My position, my ending position, minus my starting position. Okay? Does that make sense? All right. Now let's consider total distance traveled. This is different. It's related but different. Did I travel 3 feet? No. I traveled a long distance, didn't comparatively. I went all the way down there, all the way around, came back up. I even passed my starting point and then went back. Right? So, total distance traveled was not simply ending position minus starting position. Okay? We okay so far? All right. Total distance traveled is a little more complicated. Let's say that this graph, let me draw right here. Let's say that this graph represents an object's position over time. Let's say that first it starts out, let's say it has a position of 4. Let's say this is a position of 4. And then it moves this way. It moves to the right. It goes this way. And then it turns around and moves to the left. And then it moves to the right again. And this is where it ends. And let's say that it ends at, let's say that it traveled for 10 seconds. And after 10 seconds, it has a position of 7. What is the object's initial position? 4, right? X of 0, right? X of 0 equals 4. What is its ending position after 10 seconds? 7. So x of 10 equals 7. What is its displacement? 3. We just take x of 10 minus x of 0. 7 minus 4 is 3. Okay? That makes sense? Now we want to understand the total distance traveled. Yes, sir?
So when you do displacement, it's not, say it ended at like 3, would the displacement be -1? Or would it be the absolute
Yes, it
value?
would be -1. Yes. Which would imply what?
That it moved in the negative direction.
Negative direction. That's right. It is 1 foot to the left of where it started. That's exactly right. Displacement can be negative. Now, you could say the displacement was -1, or you could say 1 foot to the left. Yes. Okay, good question. It's a very good question. All right, so now, did it only travel 3 feet? No. Let's say, for the sake of argument, that this point up here is, I don't know, 3, 9. And let's say that this point down here is 8, 1. So we've got 3, 9, and 8, 1. More specifically, x of 3 equals 9, and x of 8 equals 1. What are probably the most important points in determining total distance traveled? Maximums and minimums. What happens at the maximums and minimums? Changes direction. Now, can we know it changed direction using our direction function? What function is our direction function? Velocity. Are you guys, I know, I'm here, I got it here with Marquise. Are you guys following along? Can we think of velocity as the direction function? What about velocity tells us our direction? The sign, right? And velocity is the derivative of position, which is also the slope of position. And what is the initial slope here? Positive, right? And then the slope is negative, and then finally it's positive. So, when does it stop being positive? At the maximum, right? Where it changes direction. Where velocity equals 0. Right? Where the derivative equals 0. Okay? So positive velocity, 0 velocity, negative velocity, 0 velocity, positive velocity. Right? In order to do total distance traveled, what you have to do is you have to split up your direction pieces. You basically have to do a displacement for each directional motion. How many directional motions do we have here? 3. We have an up, and then a down, and then another up. And if we have an up, and then a down, and then another up, you know how many pieces we're going to need to calculate total distance traveled? We're going to need to do 3 pieces. We're going to need to do all of the rightward motion, then all of the leftward motion, then all of the rightward motion. So how far, in its initial movement to the right, how far did it move? It moved 5. And the way we're going to find that is we're going to do x of 3, where the maximum is. X of 3, I heard somebody say it, minus what? X of 0, right? And that's going to be our first piece, right? Then we're going to add to that. That is a distance traveled. It traveled 5 here, right? Now, this is a little funky, this next piece. Go ahead. No, just tell me what you see, even if it wouldn't matter to me, Jasmine. You went, and that's one of the most important parts of learning is when you get the, what do you see? Yes, if we do the minimum minus the top, here we go, x of 8 minus x of 3. No, this is good. X of 8 minus x of 3, right? But in this particular case, x of 8 is 1 and x of 3 is 9, and 1 minus 9 is negative 8. Right? Well, it means that it moved 8 units to the left. Right? Correct? It moved 8 units to the left. Am I going to subtract 8 from the 5? I mean, even though it traveled 8 units to the left, we want total distance traveled. We don't care what direction it moved, do we? We just care that it moved 8 units. So we want an absolute value. Yep. What you're going to do is, technically, you should be doing the absolute values of all of your displacements. Now, this one was already positive, so we didn't technically need to do the absolute value. But now this one's negative. So it's got to be positive 8. And now if we do the last one, what's our last displacement piece? X of 10 minus x of 8, right? And then we would need to do the absolute value, although it's going to be positive, right? Which is 7 minus 1, which is 6. And so 5 plus 8 plus 6 is 19. So the total distance traveled was 19 units. First, it traveled 5 units to the right. Then it traveled 8 units to the left. Then it traveled 6 units to the right.
For displacement itself, you don't have to do the absolute value.
Correct.
It can be
That's exactly right. Total displacement
just in general.
does not ignore position, or it does not ignore direction. Yeah. See now, watch what if we didn't do the absolute value, watch what would happen. 5 minus 8, negative 3, plus 6 is 3, which is what displacement is, right? Okay. So really, the only difference between displacement and total distance traveled is that total distance traveled does the absolute value of all the pieces. And displacement doesn't. But no, you don't have to do this. I can see it in your eyes, Randy. No. I'm saying conceptually the only difference. But practically, displacement very simply is, in this case, x of 10 minus x of 0, which is going to be 3. Very simple. Yes, exactly. A displacement formula is a shortcut. Do you also notice, what does this also look like? It does look like slope. Missing what? What is it missing? Over b minus a. It's missing the over b minus a. So displacement is basically the change in y. It's the change in y. That's all it is. It's the numerator of the slope formula. Yeah. It all comes together. But listen, folks, if you're not working on this constantly, it's not going to stick. Okay? We don't have much time left. RCA, you guys got 8 minutes. And, you know what? Just work it out with them later. I forgot. I was so into it. Your appointment was like 9:15. They'll figure it out later. Go see them later. Okay. All right. Okay. So so we covered all that. So can we do a few homework problems, or look at a few homework problems?
You mean on this? Or on
No, from last night. Yeah. I really like this one. I really like this problem. It's the launching of a rocket. This is a great problem for understanding velocity graphically and position. All right, I'm going to put the graph up here, and then we're going to we'll talk about the problems themselves. Hang on, let me move this over a little bit. Okay, this is what the problem says. If you look at this, is question number 18. If you're viewing from somewhere else, go in the textbook and look at question 18 on page 137. Okay, so there's the graph. It says this graph shows velocity data from the flight. What flight? Well, it says when a model rocket is launched, the propellant burns for a few seconds, accelerating the rocket upward. After burnout, the rocket coasts upward for a while and then begins to fall. A small explosive charge pops out a parachute shortly after the rocket starts downward. The parachute slows the rocket to keep it from breaking when it lands. And then this graph is the velocity. This is the velocity data for the rocket. Okay? Now, let me tell you what this is not the graph of. This is not the position graph. It's not showing it going up and then falling and then bouncing off the ground. That's not what this is showing. Okay? This is the velocity data. So first, the first question says, part A, how fast was the rocket climbing when the engine stopped? What does how fast mean? Speed. What is speed? Absolute value of velocity. Looking at this graph, can we tell when things happened to this rocket? What happened at 2 seconds? Maximum what? It's at its maximum velocity. That's when the propellant stopped burning. Now, did it change direction at time 2? How do we know when it changes direction?
Oh, no, it stopped at time 2.
Right, what's that? It didn't stop.
It reached the maximum.
No, that would maximum velocity. But if this is velocity, after time 2, is velocity still positive or is it negative? Still positive, so it's still moving upwards.
Oh, okay.
It's just moving upwards at a slower speed because the propellant stopped burning.
Oh, and then the negative. I didn't.
Correct. There you go. Look at the 0 there. It doesn't change direction until when?
0.
Until velocity 0, but time 8. What happened at time 8?
It approached H max.
It approached H max. Gravity got hold of it, didn't it? And then what happened? It started falling. The slope you're looking at is the acceleration of the object. Do you see that straight line right there? That's gravity. That's the acceleration. It's negative acceleration, grabbing a hold of the rocket and pulling it down. Now it's going up. Something can be going up and gravity is still pulling it down, but it's just because it still has enough force to keep going up. But at time 8, what happened? Changed direction. Gravity took control and started pulling it down. Okay? What do you think happened at time 11 there, around time 11? The parachute popped out, right? And is the force, is it still going down? Yes, it's still going down because it has a negative velocity. Slower. That's right. It's going down slower. Okay? It was picking up speed in the downward direction, and then positive acceleration was applied that slowed down its descent. I know. See, that's it. Jasmine, that was beautiful. Thank you for saying that. Jasmine said she wants this to be a position graph. I know you want it to be. Yes. But that's one of the reasons why this exercise is so good, is it helps you remove your paradigm of position from velocity. You know what would be really good? Would be to draw a position graph based on this. I'm not saying you have to do it. I'm just saying it would be a really good self-exercise. RC, you guys got a minute and a half, okay? All right, it says, let me see if there's anything else we didn't answer. Yes, sir.
What day are we on? Is
We're
it
on.
23?
This is 23. Yes.
All right.
Today is day 23. Yep. Oh, you know what? Since we'll go ahead and wrap up, and I'll tell you guys something I want to tell everybody. Can you guys come over here, just the two of you, and I'll bring everybody else over here in just a minute. I want to show you something on my webpage that I just added. It's wonderful. Just Randy and Marquise, come on over here. I'll show the rest of you guys in just a minute. Can you shut that off? Wait, ready? Hit the red button now.